Have you ever clicked buy now on something and just wondered about the incredible invisible journey that package takes to get to your door? Or how a city even begins to decide where to build its next subway line? Well, today we're going to pull back the curtain on the hidden mathematical logic that brings order to all that chaos. The very logic that makes our modern world possible.
I mean, the sheer scale of it is just mind-boggling, right? How does a company possibly figure out the single most efficient way to get millions of different items from countless factories to warehouses and finally to your front door, all while keeping costs as low as humanly possible?
Well, the answer isn't some kind of magic trick. It's all thanks to a powerful field of math called network modeling. And let me tell you, these models are the secret weapon that companies use to solve some of the most complex logistical puzzles you can imagine. Let's start with the basics.
So, to really get our heads around these models, we first need to learn to see the world the way they do, as one giant interconnected network. And any network, no matter how complicated it looks, is really just made of two simple parts. It all boils down to two really simple ideas. First, you've got nodes. These are just points on the map. Think cities or factories or even your own house. Then you have arcs. These are just the lines connecting those nodes. You know, the roads, the flight paths, the internet cables. Nodes and arcs. That's it. Seriously. These are the fundamental building blocks for everything we're about to explore. All right, so we've got our building blocks. Let's put them to work with our first real-world puzzle, the transportation problem. This is a classic challenge in logistics, one that basically every major shipping company on the planet has to solve every single day.
So, the mission here is pretty simple, right? You've got factories that can supply a certain amount of stuff, and you've got warehouses that have a certain demand for that stuff. The model's job is to figure out the perfect shipping plan to meet all that demand without going over the supply, and, this is the key, doing it all for the lowest possible cost.
But, this goes way beyond just your daily shipping schedules. This model can help companies make these huge multi-million-dollar decisions. For instance, let's take a look at the Hargrave Machine Company. They needed to build a brand new plant, and they had it narrowed down to two cities, Seattle or Birmingham.
So how in the world do you make a choice like that? Well, you don't guess. You run the numbers. They use the model to create two what-if scenarios. Scenario 1 calculates the most efficient shipping plan for their entire network if the new factory is in Seattle. Scenario 2 does the exact same thing, but assumes the factory is in Birmingham.
And the model gives a definitive, data-backed answer. No ambiguity. Building in Seattle will save the company $37,000. See, it turns this massive, incredibly complex decision into a simple comparison by finding the absolute best outcome for the entire network, not just one little part of it.
Okay, so we've seen how to move goods around efficiently. But what if the things you need to organize aren't packages, but people, or machines that need to be assigned to specific tasks? Well, this brings us to our next puzzle, the assignment problem.
Yeah, you can really think of this as a kind of high-stakes matchmaking service. Instead of moving lots of items from one place to another, you're trying to make perfect one-to-one matches. And the goal is always to find the combination that gives you the best possible outcome, whether that's minimizing cost or time or whatever you're trying to optimize for. Let's take the Fix-It shop. They've got 3 workers and 3 projects. This table here shows the estimated cost for each worker to do each different job. Now, you could try to figure out the best combination by hand, but as soon as you add more jobs and more people, that becomes an absolute nightmare to figure out.
But the assignment model just slices right through that complexity. Instantly, it determines that Adam should get Project 3, Brown gets Project 2, and Cooper gets Project 1. The total cost? A measly $25, the absolute lowest cost possible. The model finds the perfect, most cost-effective match every single time.
So, we've moved things from sources to destinations, we've assigned people to jobs, but what if the goal is totally different? What if you just need to connect everything in a network together for the lowest possible cost?
This is a whole different kind of puzzle. You're not trying to find a route from point A to point B. You're actually trying to build the network itself. This is called the minimal spanning tree problem, and it's absolutely essential for building things like power grids or computer networks efficiently.
And what's amazing is just how simple and intuitive the solution is. You just follow 4 steps. Ready? 1. Pick any point on the map to start. 2. Connect it to its closest neighbor. 3. Now find the closest unconnected point to your new growing network and connect that. 4.
You just repeat that last step over and over until everything is linked up. That's it.
And boom, check out the result for a construction company connecting a new housing development. Just by following those simple steps, the model found a way to connect all 8 houses using the absolute minimum amount of cable possible, just 1,600 feet. No guesswork, no waste, just pure efficiency.
All right, these examples are cool and all, but what does this look like when you scale it up, like on a global scale? What is the real-world impact of applying these network models? Well, let's take a look at one of the world's largest delivery companies.
TNT Express. These guys handle over 4 million packages every single week. Talk about a monumental logistics challenge, right? So they turned to operations research and these very network models we've been talking about. The initial results were so ridiculously good, a cost reduction of over 6%, that they decided to roll them out across their entire supply chain.
And what was the result? Get ready for this. 207 million euros. That's how much they saved in just 3 years. We're not talking about a small improvement here. That's the kind of impact that completely changes the game for a global corporation. But here's what's so incredible. The benefits weren't just about the money. By making their routes more efficient, they also dramatically cut their carbon footprint, slashing CO2 emissions by 283 million kilograms. So it's a massive win for the bottom line, and at the same time, a huge win for the planet.
So, when you step back and look at the big picture, it's clear that network optimization isn't just some abstract thing for mathematicians. It is a powerful, practical tool that's constantly working behind the scenes. It really is the invisible engine of our global economy, quietly making everything more efficient, more affordable, and even more sustainable.
It really makes you wonder, doesn't it? We've applied this network thinking to shipping and logistics and gotten these incredible results. But what other complex systems could we fix? Healthcare, food distribution, the flow of information online. Once you start seeing the world as a network, the possibilities for optimization are just endless.